Yes, yes, I did. All right. Testing, testing, great. Wow, looking at lecture attendance, you'd think that there was a project due soon. I hope everyone here is at least a good degree of the way done with project 2, if not done completely. Okay, I want to ask, what's people's comfort level with the pace that we've gone at so far? Again, give me a thumbs up if you think we're going at a good pace. Sideways if you think it's going, you know, a little bit fast, and thumbs down if you think it's going way too fast. Okay. Okay, so I think that most folks generally seem to feel like we're going at an okay pace in lecture. That said, I will warn you guys, today's lecture is going to feel very, very dense. Okay? We're going to be going over join algorithms. And I'm going to be honest, sometimes there's just not a very easy way to, you know, avoid the formula burst that you might see. And now that doesn't mean that we're only going to go with rote formula memorization and stuff. It's just that this lecture happens to be one of the denser ones in the course. Okay? There's a lot of different concepts we'll cover very quickly. That said, we are about a lecture ahead of pace. So if people want, we can take a bit of Monday to go through it as well. And that's totally fine. Okay? Yes? Oh, I forgot. I meant the lecture on Wednesday. Yes, Monday's a holiday, no lecture then. Okay. So a couple more people are trickling in. Let's wait for folks to get situated and then we'll get started. While I do that, let's briefly note these down. This is the schema we're going to be using, for example. This is the notation we're going to be using, okay? So bracket R is the number of pages that R takes up, the file, the table R takes up. P sub R is the number of records per page of R. The bar, the absolute value bars around R. The pipes, that basically means the number of records of R. Easily calculated through a formula that's basically P sub R times the number of pages in R. Okay? We're going to be dealing with two tables generally, reserves and sailors. Again, I'm just putting this out there so folks are familiar with the notation that we're using so it doesn't come as a blind side. Okay? And again, at any point, stop me if we're going too fast. But let me try to motivate a little bit of today's lecture. So you guys have already dealt with a lot of the joins in your first project, right? Or in terms of writing joins at least, so you know what joins are. You know, for example, that when I'm saying join two tables together on a key, what does that mean? You know exactly what that means now, right? That you search pairs of records across the two tables for matches on the condition. So you're all familiar with that now? And today we're not really going to be talking about what joins are. We're going to be talking about how the DBMS actually, executes them. What are the algorithms used to execute these joins? Okay? And those algorithms could be block nested loop join, index nested loop join, whatever. We'll go through what those algorithms are. So at the heart of it, the simplest thing about joins is you're taking, if I'm joining two tables R and S on a condition, the simplest thing is that you take every record in R and every record in S and you do a pairwise comparison to see which pair of records yields a match on the condition, correct? Everyone familiar with that? That, at the core of it, is what functionally a join is. And you can see that here. We've written it in a loop for each record in R, for each record in S. If there is a match, denoted by theta of R sub S, theta of R sub S is a join condition. If that join condition yields true, we're going to basically add R and S to our output buffer. We're going to yield R and S as a tuple. Okay? And so you can kind of see here what that animation looks like. And you might think, well, that seems all simple, but isn't that a little bit of a waste? Might it not be true? Does anyone notice here, what's so inefficient about this? Yeah, you have to loop through all of the pages of S for every record of R. I'm holding a record of R constant, and then I'm looping through every single record in S. And at some point, that just becomes way too inefficient. How inefficient? Well, let's see what the cost is here. 50 million IOs. Wonderful. Now, that's just clearly infeasible. We can't work with this. This is nice for conceptualization, but we haven't even dealt with the output cost yet. And the IO here is already like 50 million. That just doesn't work. Okay? Because the cost here, we have to read in all the pages of R, plus for every single record in R, we have to read in all of the pages of S. So maybe let's do one better. We know that to read in a record of R, we have to read in the entire page, correct? So while that page is in memory, why don't we do something smart here? We'll just say, fix a page in memory, and then for that page, let's read through all of the pages in S. Fix a page of R in memory, and then for each of those, for all of the records there, we can basically do something a little bit interesting. I'm going to skip past this for now. Let's see. How does page nested loop join work? So now what we've said is we're going to deal in terms of pages of R and S now. For each page in R, we're going to loop through all of the pages in S. Okay? So what does that mean in the inner loops? In the inner loops, that means is, for each page of R, for each page of S, now we have a pair, R and S in memory. For each of those pairs, iterate through. Now we're going to hold a tuple of that page constant, and we're going to scroll through all the tuples of the page S that we've loaded in memory. And so, every page in R now only gets loaded in one time. Correct? Which is a lot better than previously when we were basically loading in a new page every single time. Right? Every single page of S here only gets loaded in once for each page of R in memory, basically. Which is better than before, because before we had, you know, oh, well, there's a record of R you hold constant, and then for each record we have to load that page in. So you could see how that kind of becomes a little bit inefficient. So what does that loop say here? Let's visualize it out. Hold the page constant, read through all of the pages in S. And then in that page, we're going to basically, for each tuple, read all of the tuples in S. So automatically, folks can see how much more efficient this is, correct? Like, this is way better. But great, we've cut down the cost quite a bit. But that's still a lot of IOs. 500,000 IOs is still a huge deal. So how do we do better? Our question is, can we improve this? And now I want to bring up an important point. I talked a lot in last lecture about our buffer pool. Remember the B-2 pages in memory or the B buffer pages in memory? We've talked a lot about that in the last couple of lectures. Up until now, I haven't brought that up yet. All I've said is, oh, hey, well, instead of, you know, loading in a new page of S, or a page of S for every single record, maybe let's just load in pages of S per page of R. But here's something we're forgetting. Our buffer pool can hold B pages in memory at a time. So why is that relevant, you might say? Well, take a look at this loop. What is the factor that determines the cost? What is the single biggest factor that determines the cost? The single biggest factor determining the cost is how many times do we have to read in all of S? Is that part clear? How many times do we have to read in all of S? If I have to read in all of S per tuple, prohibitively expensive. If I have to read in all of S per page of R, like now, better, but still very expensive. So from last lecture, what do we remember? We have to have this concept of an output buffer, yes? We need to have an output buffer to actually store our results. We need to be able to flush the yielded tuples to that output buffer, and then as that output buffer fills, we flush it to disk. We also need an input buffer. In this case, we would at least need 2 input buffers, right? We need an input buffer for R. We need an input buffer for S. Okay, so I've used up 3 pages right now. Maybe let's go one better. We have B pages in memory. And I want to reduce the number of times I read in S. So wouldn't it be nice if I could just say, hey, let's try to fill as many pages of R as we can in memory. Let's fill in as many pages of R as we can in memory, and then we'll basically say, oh, well, now that that R block is in memory, I'm just going to take each page of S and then compare all the tuples in that block of R to all the tuples in that page S. Now, wouldn't that be a lot better? Because now I'm only reading in S once for each block. And that's the idea behind block nested loop join. Okay, and that basically says for each block of B-2 pages of R, we're going to read in S on a page-by-page basis. And then for all the matching tuples in the page of S and the block of R, you're just going to yield the resultant match and put it in the output buffer. And you can see how much more efficient this is. This is now like only 6,000 IOs. And remember, we had like 40 or 50 million IOs for simple nested loop join, which dealt with only records. We had 500,000 for page nested loop join, which dealt with only pages. Now that we're dealing with blocks, we've reduced the number of times that we need to read in S. And so, we've simplified and reduced the number of IOs greatly. And this is an incredibly powerful algorithm. This is used a lot of the time. This is a very, very good algorithm, and it's the one that a lot of people use. So if we were to go to an animation of it, you can see here that for each block, there's one arrow, basically just traversing through all of S per block of R. And this is the critical thing here. Okay. So far, is this clear to everyone? Okay. As always, thumbs up, thumbs sideways, thumbs down. Okay. Now, before I jump on to the next part, I want to now take a brief aside to address something. You've noticed that the formula here is something like pages of R plus R divided by B minus 2 times S. Yes? And what that means is basically the outer, you can see from this formula that if I switched around which table was the outer table, R or S, consequently my cost would also change. So it really depends which table is the outer table in IO cost, and you're going to have to decide when you're executing joins, which table do I want as the inner one. Let's go back to simple nested loop join, and I'll give a very, very dumb example. If I change the join order here, this thing cost 50 million IOs when I had R on the outside. If I put S on the outside, my cost would change appropriately. Because the math functionally changes. In the case of simple nested loop join, I was scanning, if R was on the outside, you're scanning S once per R tuple. Now if S is on the outside, you're scanning R once per S tuple. Ergo, if S has fewer tuples than R, you could kind of see how costs might change. So changing the join order does have an impact on your overall costs. And that's something to keep in mind as we move on to later units. But in any case, now let's talk about something a little bit more sophisticated than block nested loop join. And to be clear, that doesn't mean it's better. That doesn't mean this is always better. Block nested loop join is a very, very good algorithm. A lot of the times, people might just use it because it's the cheapest. Ultimately, it matters what is the cheapest thing for us on the whole. Our simple goal is to reduce IOs. Whatever lets us reduce IOs in the end is what we like to go with. And now that doesn't always mean just the join that has the least IOs, right? Because there's many parts to the query other than the join. So if, for example, you want to sort the result, you might want a join that yields a sorted output so that you could save on the sorting cost later on. These are all factors to weigh on, to keep in mind. But anyways, so as to not put the cart before the horse, let's talk about index nested loop join. So let's say that I had an index. This is, at its simplest, this is what a join is. But if I had an index Remember something about simple nested loop join that kind of sucked? To find the matches, I had to scroll through all the pages. But in an index, this is different. Why? Because an index allows you to do lookup on tuple values. So we can actually leverage that here in a very powerful way. For each tuple in R, we can look up that tuple in an index if we have one. And we can check to see matches. And we check for matches, and then as the matches are yielded, we put them in the output buffer. But this is a lot better than simple nested loop join, because now I'm not scrolling through all the pages of S for every single record of R. No, now for every record in R, I'm just looking up its value in an index. And we know that indexes tend to be pretty short in real life, right? Like maybe 2 to 4 in height. So I don't actually have to, a lookup itself isn't all that costly, so to say. So this is what index nested loop join looks like. That's the loop, and obviously in your inner loop, you'd really just be looking in the index. And now, the cost of this. This is probably the worst part about index nested loop join. It's really hard to calculate the cost of this thing because it really depends on the alternative of the index that you have. Okay? Because the cost of this thing is, you have to read in obviously all the pages of R, plus for each tuple of R, you have to search for matches. And so the question is, how many matching tuples exist per record in R? And so generally that's the formula, R plus number of records of R times the cost to find the matching tuples, the cost to traverse the tree. For alternative 1, that's pretty easy. It's just the cost to traverse the tree from root to leaf. Right? Because there's no references in alt 1. In alt 1, your data is stored at the leaf nodes, as we went over before. But if you have alternative 2 or 3, which is storing by reference, then the cost gets more annoying. Then it's the cost to look up the RIDs, which is traversing the B plus tree from root to leaf, plus the cost to retrieve the records from the RIDs, which for a clustered index is 1 IO per page of matching tuples. For unclustered index, it's up to 1 IO per matching tuple. Some of you may remember that from the lecture on B plus trees, indexes, and refinements. Does anyone remember when I had in the video or the slides that I had where I kind of showed how searches might differ in cost based on clustering or unclustering? Same way here. It really makes a difference. Okay? So I'm going to skip past the cost calculations on this one because the truth is, this is not something that ever goes over well in a lecture. This is something where it's really, once you have the overall outline, it's best to just sit through and work through it in calculation. We're going to do that in discussion. Okay, there are questions in discussion specifically designed for this. But if I introduce this now, I don't want to risk people getting caught up too much in the calculation details. So for now, we're going to skip past the costs in the specific numbers. Just know that the cost of index nested loop join needs to be dealt with on a per index basis, depending on the alternative, depending on the number of matches you have. Okay. So, we've dealt with two pretty different joins, but at the heart of it, two joins that that still obey the same basic structure, right? For all the records in R, go through all the records in S, in a sense, Okay, it's not really how it goes, because in index nested loop join, you leverage the index specifically, but basically we were going on a per record basis for R in the past two. Yes? And that's just one way to think of it. Now, let's maybe try to continue our idea here. Let's try to continue that idea, but let's think about some more properties we can leverage depending on the file that we have. If we have a sorted file, if we have two sorted files actually, it turns out that we can leverage those two, the sorted structure of those two, to yield a very efficient join. Okay? So this is called sort merge join. It's going to have two phases. Phase one, you're going to sort R and you're going to sort S. And phase two, you're going to scan both R and S and emit any matching pairs of tuples. And so you can imagine, a lot of the times our tables are already sorted. If our table is already sorted, this is a great join to use, because you avoid the cost of sorting them, and now you can just scan the two and emit tuples that match. So you might ask, well, why is the scanning phase so efficient? You keep mentioning that it's efficient, but why? So let's go through this. Let's walk through sort merge join. Okay? Let's assume that the two tables are sorted. We're not going to sort the tables. We did that in the last lecture. So now let's assume that the tables are sorted, and before we run through a demo, let's take a look at something here. Okay. I want to point out something. Notice that it's sorted on SID. So, if my SID is, let's say I have like a pointer to a current record on both R and S. Let's say R's record has an SID of 22 in this case. And S's record has an SID of 28. Now you know that this table is sorted in descending order on SID. Do I actually need to read in all of S to figure out that there's no match for the record in R? Okay, I see some people shaking their heads no. Why? Yes? Exactly. One of the SIDs is obviously far behind the other. If S's SID is already 28, and like that's the first record here, you know that nothing below that can possibly be 22. So you're like, oh, well, I guess I can just skip past SID 22 because there's obviously no match for that. So you could go on to the next one. And so you see, when you have these two pointers, you can kind of compare the two and basically just advance whichever one is less, because you know, like, oh, if this is less, if R, for example, is less than S, and I'm doing, say, an equijoin, right? If R is less than S, then I already know that there's no more matches for R that I can yield. So maybe let's walk through an example here. So we're going to introduce the concept of a mark. And what that mark is going to tell us is this. Okay? When we have a match here, 28 and 28, this is the start of a matching range. Okay? And everyone pay close attention here because the mark is going to be critical to sort merge join. This is the start of a matching range. Now it could be that that range is just one tuple. That could be the case. But you don't know that yet. 28 yuppie, 28 103. I know that's a match. But I don't know, for example, that the next record doesn't have 28 as well. So I can't just say, oh, I have a match, cool. Yield it and then let's advance R. No, you can't do that. So then you might say, oh, okay, well, what if you, what if you like held R constant and then you scrolled through S? And then once you finished S, you just keep S where it was at the finish, and then you advance R. But what if the next record in R actually had a value of 28 as well? Now you've just skipped through all of those matches of S. So we need something better. We need a way to indicate we've begun to scan a matching range. And then we're going to basically scan all the matches for 28 yuppie. And then when we're done scanning matches for that, we're going to reset S to the start of the matching range. And then we're going to advance R. And that'll basically protect us from skipping anything. So we'll say, okay, this was the matching range for R. And now we can move on to the next record. And if that was the same value as the previous one, then we'll use this range. Otherwise, we can just advance S as needed. Okay, so here, we've gotten to 28, 28. Now we're going to mark S. So if R is equal to S, which it is, we're going to yield a result. We're going to advance S, not advancing R yet. Advance S, return the result. Okay. Now, next is, this is the function next, right, in an iterator. It's going to be called again. So mark is set already. Okay, it means that we're in the middle. You can kind of think of it like we're in the middle of a range almost. We're still scanning through a range. Okay, so mark is set. Is R equal to S? Yes, it is here. Okay, and mark, by the way, is denoted by the black arrow. Is R equal to S? Yes, it is. So we're going to yield the result, advance S, and return the result. Now, we come back here. Mark is still set, but R is not equal to S here. So now we've got an indicator that our range has ended here. So we're going to reset S back to the start, or back to mark. We're going to reset S back to mark, and then we're going to advance R to the next record. Okay? And now that we're not in the middle of a range of matches anymore or whatever, we can just set mark to null. Okay, because mark was there mainly to make sure we didn't lose our place in the middle of emitting matches. So now that that's done, we can set mark to null, and we'll repeat this. So here, 31, lubber, 28, 103. Is R less than S? No. So we're going to hold R constant. We're going to advance S. So we advance S, and then now we get to 31, 101, which is a match. So going through that again, we're going to set our mark. Okay, and now now we've ended the range of 31. So, what do? We're going to reset S to mark, advance R, now set mark to null. And now this is the reason we had that mark in the first place. This is the exact reason that the marking began to become a thing. Because 31 is duplicated in this table in terms of SID. So we need to make sure that whatever matches we emitted for the record above this, for lubber, that we emit it for lubber 2. Okay? So we're going to repeat that process once again. And then, having yielded those matches, we'll advance R and then advance S accordingly. And yeah. Is the picture of sort merge join clear to folks? Okay. So what's the cost of sort merge join? What's the cost of sort merge join here? Let's think about it. It's the cost to sort R plus the cost to sort S plus, in general, it's going to be just R plus S, because the merge scan just requires us reading through R and reading through S. And we generally assume, like that we don't have all that many duplicates, so we don't need to mark and reset all that much. So typically this last phase is like just R plus S. You have one scan of R, one scan of S. You typically assume that the matches, that the duplicates are like kind of in a sorted file, they'll be more or less on the same page, right? I mean, unless you have a lot of duplicates. And if you have a lot, if there's just like, if two tables basically just have all duplicates, they all match, yeah, then you might end up in a nightmare scenario where you have to read through the entire table of S for every record in R. But that's very unlikely. And if that happens, you might have other problems in your data. So a random question we might have is, how big does a buffer need to be to sort R and S in 2 passes? The answer for that is, we might remember from the last lecture that in general, on the order of how many pages can you sort in 2 passes? Does anyone remember? It's like on the order of B times B minus 1. Okay? So we can do some math here, and we can see that if the buffer is on the order of, the square root of RS, then we can generally sort it in 2 passes. I just got a lot of surprised Pikachu face expressions from that, so let me walk through that again. Remember that in general, let's just deal with B squared, because I don't like saying B times B minus 1. You guys all know what I mean. Remember that like if R was around the order of B squared, we could sort it in 2 passes, correct? That's from last lecture. If you want to figure out how big B needs to be, you just take the square root of B squared equals R, and you have B equals square root of R. Now, of course, in this case, you need to make sure that you can sort both R and S in 2 passes here for the question that we had asked. So it would be square root of the max of R and S. So you might ask, well, couldn't we join first and then sort later? If we want our output to be sorted, why don't we join first and then sort later? So let's try it. Let's first execute BNLJ. We know the cost of that. And then let's sort it. In this case, as we work the numbers out, it turns out to be about 9,500 IOs. This is easily verifiable by a formula check, but for now, let's just take our word for it. Okay, this is, you first do BNLJ, and then you can kind of assume, to be generous to yourself, that it would take maybe, you just need to sort R, and then you'll, the cost of sorting R is approximately the cost of the join, or cost of sorting the join result. So you might have about 9,500 IOs, 10,000 IOs from this. Now let's compare that to sort merge join. If we sorted first and then joined later. So the cost of sorting R here would have been 4,000. The cost of sorting S would have been 2,000. And then the single scan R plus S would just be 1,500. So we can clearly see that sorting and then joining is generally better. It helps us leverage properties of the file. We don't need to revisit records, for example. And that's something that's really good here. So that, in general, would be more cheap than doing a block nested loops join and sorting the output. Now you might ask, why don't we always just do sort merge join then? Well, remember the cost of B and LJ here was 5,500 IOs, right? If we didn't care about the output being sorted, you know, one of them can still be more efficient than the other. Block nested loop join is still good. Just, it's not always what you want. Right? It really depends on what you're trying to accomplish. Okay. Now I want to show you a refinement, and then I promise we'll take like a 10-minute break because it seems everyone is exhausted because there is way too much stuff presented here in one go. Okay? Okay, so this is something you probably want to keep in mind every time you think about sort merge join. So it's a very good optimization, and what it basically means is you're going to take the last pass of sorting, and then in that last pass, if you can, you're going to actually do the scan phase of sort merge join. Okay? I know these slides are dense, but the reason I've put this much text on it here is because there's a lot of information, and some people hear better just when I talk through it. Other people actually like to follow along the logic on the slide, which helps if you tune out for like 30 seconds and then come back in, right? It's okay, we've all done it. Okay, so how does this work here? Let's make an assumption. Let's make an assumption that we have enough buffers to accommodate one buffer for each sorted run of R and one buffer for each sorted run of S. Okay? And then obviously you need your one output buffer, so the number of sorted runs of R plus the number of sorted runs of S has to be less than or equal to B minus 1. That's the condition we need to deal with. Now that we have that, we can actually just do that merge phase. We can do that scan phase. We can basically just say, now that these runs all have their minimum page loaded in, I can kind of like, I guess, to start with, I could like take the minimum record of R and the minimum record of S and kind of do my scans there, right? Or I could, for example, for each, I can basically, I don't need to actually finish sorting R and S to begin my actual merging scan. Okay. So while we're merging the R runs, essentially we always know the minimum value of R in memory. And at the same time, at any given point, the final sort of S, we always know the minimum value of S in memory. And because these are sorted runs, I know that each run's minimum elements are going to be in memory. Correct? So if each run's minimum elements are going to be in memory, well, that's all I need. Right? You know, assuming I don't have something crazy like a whole ton of duplicates, this actually becomes really nice. Because for a record in R, I just scan through the runs in S, I see like, I kind of repeat my merge scan procedure there, and I yield the matching tuples. And then I move on. Okay? So let's take a break of about 10 minutes. And then let's begin again for the last thing that we're going to cover today, which is in-memory hash join. Okay, I'll come around in just a second. Does this microphone work? Testing? Yes. Okay, great. All right. So let's move on to probably the last couple of joins that we'll talk about today. Okay? Here's something that people might want to remember. Hashing is really, really good for lookup. Yes? We're all familiar with that, right? From 61B. So, if we leverage that property, maybe we can make our joins faster. So let's deal with a very simple, simplistic, easy case. If one of our tables is pretty small, let's say it's like, let's say it can fit in let's say it can fit entirely in memory with some pages left over. Okay? Let's say for example, it's just B-2 pages long, for the sake of example. We can do something really nice. We can build a hash table in memory on that tiny table. Let's call it R. Okay? And then, what are we going to do? We'll say, okay, now that I have like a hash table built on R's records, which, by the way, only took me R IOs, right? Like the number of pages in R. So it's very cheap so far. What would we have done in the past? In the past, we might have dealt with sort merge join or block nested loop join. Let's try something a little bit different. Let's do this. Let's build a hash table in R, and then we have our input and our output buffers. Let's stream in S into the input buffer, and we're going to do a lookup in the hash table for each record of S. And as we find matches, we'll yield them and put them in the output page. So you're going to load all of R into a hash table, and then you're going to scan S. And as you scan S in, you're going to probe the hash table for matches. And now because this is hashing, this is an algorithm for equijoins and natural joins. But as long as this memory requirement is fulfilled, where R is less than B-2 times the hash fill factor, we're good to go. But, now you might think, well, that's a really simple algorithm. Why wouldn't we do that all the time? And here's the answer. What if R doesn't fit into memory? What if neither of these pages fit into memory? What do we do? If neither of these pages fit into memory, we'll need to work on maybe a way to reduce to this. Remember that thing that I brought up in hashing last lecture, if anyone remembers that, where I said like, you know, when you're partitioning a file, let's say you're partitioning R, let's imagine, you know, you send it into B-1 buckets. Let's imagine each one of those buckets is now treated like a subfile. And you can just continue your partitioning algorithm for each subfile until it's small enough to fit into memory. And when it is, you can just build your in-memory hash table. What if we did something like that here? What if we said, well, I can't fit R or S into memory, so let me try hashing both R and S and partitioning them into smaller and smaller groups until a partition is actually, you know, until R or until one part of the partition is small enough to fit into memory. Then I can reduce it to this naive in-memory hash join case, and I can execute this algorithm. And so that is an algorithm that is called Grace hash join. Now every semester, someone asks about Grace Hopper join. I don't know what that is. I don't know how people get it, but people always ask, what is Grace Hopper join? I'm here to tell you I have no idea, but please don't ask that on Piazza because all that's going to get is a bunch of apocalyptic laughter from TAs who are now terrified that they didn't teach hash join. So it's called Grace hash join. And basically, the point of it is to reduce your subpartitions to be small enough so that you can reduce to the in-memory hash join. You're going to have it consist of two stages. The partitioning phase, where you break up the tables to be smaller and smaller by hashing them. And then, once the partitioning phase is done, there's the build and probe phase, which is just naive in-memory hash join, really. And so how do you know when your partitioning phase is done? Let's go through that. So you might remember external hashing. This is the diagram. And this is what Grace hash join kind of looks like. You divide, and then you're going to conquer. That's your in-memory hash table you're building with a one input buffer for the bigger file and one output buffer for your output. So right here, right now, before I go on, people can kind of see how Grace hash join is working. You're hashing by partitioning first, and then in the final phase, instead of conquering both tables, instead of building the in-memory hash table for both, you build an in-memory hash table for the smaller of the two, and you probe the larger table in the partition. You probe the larger table, or you stream the larger table in to the input buffer, and then you probe on the hash table. Okay, so like a partition has two parts right now, right? There's a partition, and it's going to have like part of R hash to it and part of S hash to it. You're going to take whichever one's smaller, build an in-memory hash table, and then stream the larger one in. And as you stream the larger one in, you're going to probe its records. You're going to probe the hash table for R, or the hash table for the in-memory, basically. Okay, and remember that there's no size requirement on the larger partition, so to say, a larger part of the partition. There's no size requirement on that bigger table. That bigger table could be as big as we need to. It doesn't matter. All that matters is that the smaller table can fit into b minus 2 pages, into a hash table of b minus 2 pages. That's all that matters. And if that condition is met, we are good to go. And so you might ask, well, how are we guaranteeing that as we're hashing R and S, that the matches for R and S don't go to different partitions? And the answer is that if we hash on the key that we're trying to join on, what we can do is we'll say, well, if we use the same hash function in R and S, then the same values will map to the same partitions by definition of hashing. Ergo, I don't lose any matches. But each partition is probably going to be significantly smaller than my original table was. Okay? Oops. So this is what the pseudocode looks like for Grace hash. And this is going to be on the slides in case anyone wants to copy it, but I'll just explain what it's saying. It's basically, this is the partition phase, the part in gray at the top, and then this bottom part is the probe phase. So just remember that it comes in two phases, partition and then the build and probe. And if you understand that about Grace hash join, you're good to go. Just remember this. you need to keep hashing a partition, a file, a partition, whatever. You need to keep hashing it until one of the two files is small enough to fit into an in-memory hash table. Okay, if you think of a partition as consisting of two parts, R and S, you need to keep hashing until one of R and S is small enough to fit into memory. And if you can do that, then you're good to go. Then you can actually just go back to in-memory hash showing. You've reduced your case to in-memory hash showing. Because in-memory hash showing was just building a table of b minus 2 pages, a hash table of b minus 2 pages, and then streaming the larger table in. Okay, so let's go through the animation now. So I have my page for S. I'm going to hash this. Then I'm going to hash R. Okay, this is just the partitioning phase. Now notice each key is assigned to one partition. Like the green star keys are only going to be in partition 1. And now notice something else. This is sensitive to key skew, just like hashing. This has the same issues. This is sensitive to key skew. So that's something to keep in mind. And something else to note is that later on in the class, when we deal with distributed computing, when we deal with parallelization, we might want to remember that each partition could be on a different disk or even a different machine. Okay, but those aside, now let's go to the build and probe phase. I've partitioned. Now let's go into build and probe. And this is what that looks like. Okay, so I take smaller of the two tables, I'm hashing it. Now I'm probing. Okay, I've built my hash table here now. I'm going to stream in the other one and probe. Okay. So give me, let's do the thumb poll again on Grace hash join and on just on hash joins in general. Raise your thumb, thumbs up, sideways, down, depending on your level of comfort with this. Okay. So let's open the floor for questions, because I think a lot of people are pretty confused. Yes?
Just for understanding, if somehow two different things map to the same thing in the hash, it would create like accidental equality here, or not?
Are you saying if, so the question was if two different values map to the same hash bucket, would it create an equality error?
Yeah, like just hypothetically in this like
No, so this, basically what's going to happen here if, so the question that was asked was, what happens if you have collisions, essentially? The answer is that generally the hash function that we want to use in the build and probe phase is going to be very, very finely grained. And it's going to be so finely grained, ideally, that there are no collisions. But if there are, at the end of it, what you really are doing is the hash function is there to get you to the correct bucket, and then you actually have to check which ones are matches. So you won't end up in a condition where you yield the wrong tuple, but you will, if there are a lot of collisions because you didn't pick a good hash function, you might have to scroll through a lot of values to eliminate which ones aren't, to actually find your matches, if that answers the question.
Yeah, so I was under the impression that during the probe when it tells us the right bucket, you just blindly match everything.
No, no, no. In the probe phase, you do actually need to do a search for which records match. The hash function will get you to the right bucket, but then once you're in the bucket, it's your responsibility to check what the matches are. Okay. Any other questions on Grace hash join? Okay, so what do folks find confusing about Grace hash join? Is it that people are not comfortable with hashing? So let me take a poll here. Give me a thumbs up, sideways down, based on your level of comfort with hashing. Okay. So with Grace hash join, I think first let's forget about Grace hash join for a second. Give me a thumbs up, sideways down, based on your comfort with naive in-memory hash join. Okay. So in-memory hash join, let's just try to simplify it to a 2-sentence snippet. And I think part of the confusion for people is just that this is such a long lecture in terms of content that by this point, a lot of people are just saturated already. And I think that's really what's happening. So let me try to distill it to a 2-sentence soundbite, if that sounds good. Okay, and obviously don't take this as gospel, but I'm just trying to summarize it. Naive in-memory hash join is basically this. You have one very small table, and you can load it into memory to build a hash table, which is really good for lookup. So you've made your equality search very easy because you have a hash table built on one table, and then your second table, your larger table, you'll just stream its pages in one by one and just check its records against the hash table for matches. In essence, think of it like this. I'm supposed to join R with S, and by some nice coincidence, I already have a hash table built on R. Now this is great because what's a join? The equijoin is telling me, find all the matching tuples between R and S. So to find a match, I use the hash table and I say, okay, yield matches for this tuple, yield matches for the next tuple, yield matches for the next tuple. So you basically just scroll through all the tuples, all the pages in the bigger table through the hash table that you built the smaller table on. And that is, in essence, naive hash join. Okay? And Grace hash join is basically naive hash join with a step before it. And the step before it is partitioning. And the idea behind the partitioning before it is basically, well, neither table is small enough for me to actually just do that hackish in-memory hash thing. Right? Neither table is small enough for me to actually build an in-memory hash table. So I need to get a little bit creative. I need to actually reduce to the naive in-memory hash case. Now the condition for that is that I have to have a table that can fit into b-2 pages of memory. Ergo, let me hash it and cut the table into smaller and smaller subtables in a sense. And then for each of those subpartitions, as I can, I'll conduct in-memory hash join for each of them. Is that going to help? Okay. So what's the cost here? There is no simple way to do this in general. You're going to have to partition R and S for Grace hash. And for each pair of partitions, when one is less than b-2 pages, you can stop partitioning. After you stop partitioning, you move to the build and probe phase, which basically involves reading R and reading S. And this has to be dealt with on a per partition basis. So this is something where you have to be very involved and you have to actually write out what's being done. How is the hash being done? What's the size of the partitions? What's the size of the table? Okay? I have some more slides, but I think part of teaching is recognizing when people are extremely saturated with content. And I think if I went through that right now, no one is gonna understand it except maybe 5 people. So you guys are free to go. We'll go through more of this on Wednesday. Have a great long weekend, everyone, and I'll see you guys all next week.